Alright, so hopefully we got a pretty good understanding of how to write compound formulas and name chemical compounds. So now we're going to get into a little bit more about what holds them together, the bonds, the chemical bonding that holds these different compounds together. We're going to start with ionic, and we've talked about a lot of this already, so that's one of the reasons why we're getting the notes this way. But first off, remember that the noble gases are the least reactive elements. They're also called our inert gases. All the other elements want to be like them, stable, and that's why they are on this quest for nobility. And as it says, the noble gases are indeed the most stable elements. Why? Because their outer energy levels are filled with electrons. Remember that that magic number is 8, except for helium. Helium only has 2 valence electrons because the first energy level can only have 2 electrons. But here you see neon, and its second energy level is filled with 8 valence electrons. So after neon, there's argon. That would be 3s2, 3p6 for neon. Krypton would be next, and that would be 4s2, 4p6 for the ending of krypton's electron configuration, etc., etc. Now, of course, these outer energy level electrons are known as valence electrons. We have talked about that several times before, so we'll be mentioning the fact that, or looking at these outer electrons being the most important ones involved in bonding, valence electrons. So our ionic bonding that we're going to focus on is going to be occurring between a metal and a nonmetal. And if you remember, our most reactive elements are the alkali metals and the halogens being the nonmetals. So let's see why they're that reactive and why they like to get along so well with each other. Well, first off, the alkali metals, they all have 1 valence electron. They are in that first group. The halogens, they all have 7 valence electrons, and they are in group 17 right next to the noble gases. So when you look at a drawing of the sodium atom, you'll notice that it has 1 valence electron. All the alkali metals look like that with 1 valence electron. And underneath that valence electron is a full energy level of electrons. And so that's why those alkali metals, like sodium, really are very reactive. They want to get rid of that 1 electron, which will make them more stable, like a noble gas. And then if you take a look at chlorine, chlorine here has 7 valence electrons, and it is this 1 magical electron away from completing the octet. And so that's why they like to get together so well, so swimmingly. Sorry, lack of a better term. But sodium wants to get rid of 1, chlorine wants to gain 1, so the halogens and the alkali metals always do a lot of bonding together. And that is going to be our classic example of an ionic bond. So as it says here, both sodium and chlorine are very reactive. When they're put in contact with one another, there is a very violent reaction, releasing a lot of heat and light. We'll see that shortly. What's left behind is sodium chloride. Now, sodium is an extremely violent reactive metal. Okay, and when it goes in contact with water, even as we saw earlier in the year, it can ignite and catch on fire. Chlorine gas is extremely toxic, used in chemical warfare, but yet we put those two together, yay, sodium chloride, we sprinkle it on our french fries, and we actually cannot live without that. So why is that so? And you see there, because the sodium chloride is made from sodium cations and chloride anions, and they are much different than sodium atoms and chlorine atoms. And that ionic compound, sodium chloride, is much more stable and not as destructive to us whatsoever. Alright, so what is happening here? So sodium loses its valence electron, becomes a positive +1 cation. Chlorine gains that valence electron, becomes a negative chloride anion. And we have an opposites attract situation here. We have opposite charges, positive and negative, coming together, and that force of attraction between those two charged ions is what we call an ionic bond. And here's kind of what it looks like visually. Sodium transfers its valence electron to chlorine, and through that transferring of the electron, we end up with those electrostatic attractions. And again, this doesn't happen one to one. We have millions, billions, gabillions of these atoms transferring electrons, and these compounds end up in those nice crystals that we've talked about earlier. Here is a fun little visual of this transferring going on that I know you're just going to totally enjoy. So sodium comes along, transfers its electron to chlorine. Sodium becomes positive, chlorine becomes negative chloride, and there's the electrostatic attraction holding them together. I told you you'd totally enjoy that little visual. So while we commonly call sodium chloride salt, table salt, chemists actually use that term to describe all ionic compounds. All ionic compounds are indeed called salts. And so that'll be a term we'll be using throughout the rest of the year. Now again, this transfer happens on a very large scale, and so we end up having these crystals that we mentioned. And so sodium chloride with its 1-to-1 ion ratio, the formula unit NaCl, sets up this beautiful crystal lattice of repeating patterns of positive sodium ions and negative chloride ions. And so we have that very nice distinctive crystal structure. So here's a nice little diagram describing how this happens. First of all, you'll notice over here on the y-axis that we have energy. And as you go up the y-axis, energy is increasing. And so here we start with sodium and chlorine, sodium atoms and chlorine molecules, because Hofbrinkel, it's a diatomic molecule. When we add a little energy, we do this to convert sodium from a solid to a gas. The sodium loses its valence electron, and then a little more energy is put in to break up the chlorine molecule so we can get single chlorine atoms. So we have an energy investment there. Once that happens, however, we reap the rewards. A lot of energy is released as the electron goes to chlorine to become a chloride ion, and then even more energy is released as those ions come together and form the very stable sodium chloride. And so you'll notice here that the crystal sodium chloride has a lower energy state than the reactants sodium and chlorine do. And so the energy level way down here is less than where we started. And that's why ionic compounds form. They're much more stable than the atoms from which they come. Now we're going to check out a little video here of what exactly is going on so we can see this diagram in action. Alright, so here is the formation of sodium chloride. See if I can get this to play. Oh, hold on. Okay, here's the video. So the first thing we're going to see is we're going to be heating up the sodium metal, and you can kind of see the distinctive orange color like we saw in the flame test. That sodium is now liquidy, and it starts to react with the green chlorine gas we see in that tube. A lot of energy is being released in the form of heat and light, and all the electrons are being transferred for the millions and millions of sodium atoms and the millions and millions of chlorine atoms. And what we're going to be left with then is the white sodium chloride on that spoon that used to be the liquid sodium metal. Totally awesome, I know. So again, these ionic compound salts are made of cations and anions, positive cations, negative anions, and they're held together by these ionic bonds. So what else? Well, remember, ionic compounds do not consist of molecules. The formula units there describe to us the ratio of ions in those crystals. And within those crystals, there are both repulsive and attractive forces existing. The attractive forces are much stronger, which holds them together. Obviously, you got the positive nuclei of all the ions pushing against each other, but the opposite charges of the ions hold the crystal intact. Now, what happens when a salt melts, which is what we say when it becomes molten, or if we dissolve a salt in water? Because it's made with those charged ions, we can end up having what's called an electrolyte. So the crystal structure of the ionic compound loosens, and the charged ions are free to move about, and the salt will conduct electricity. And that's what we call an electrolyte, a compound that when it's melted or dissolved in water will conduct electricity. This is why it's a bad idea to be swimming during an electrical storm, because of the fact that we have electrolytes, these salts in the water. Beside, there's human sweat, there's the sodium hypochlorite in the water fighting the germs, there's all those other particles floating around. Now, if you went swimming in pure water, then electricity would not be conducted through that as much. So it's the fact that you're swimming in pool water where there is a lot more of these electrolytes, or in the ocean, because we all know that the ocean is full of sodium chloride, so it's very, very conducting in the ocean. And the last little thing here, most ionic compounds are both very hard and brittle. These crystals will shatter. Brittle, get it? Peanut brittle? I know, funny. And that's just a very that's a characteristic of these ionic compounds, that they're both hard and brittle, so they're not malleable. When you hit them with hammers, they do indeed shatter. So that concludes the ionic portion of the notes. I'm going to stop the video here and just make another short little video to take you through the metallic bonding.